Hello everyone, this is Dr. Zach. For today's lesson, we're going to integrate using trig substitution. As you look at your lesson preview, there are many parts to this for triangles A, B, and C. We're going to work on triangle C together. For our triangle, we will label our missing side. The missing side is the square root of u squared minus a squared. Now we're going to write an equation using a, theta, and u. Then we will solve for u. So when we look at our problem, we know that the tangent of theta is equal to the square root of u squared minus a squared divided by a. Next, solving for u. Square both sides. The tangent squared theta is going to be equal to the u squared minus a squared, but let's cross multiply and put our a squared on the left side. Add a squared, so we have a squared plus a squared tangent squared theta equals u squared. Take the square root. We're going to use the positive value of our square root because u is the length of a side. We will have a squared plus a squared tan squared theta is equal to u. We can factor out our a squared, which gives us a times the square root 1 plus tangent squared theta. That should look familiar. We have, once we simplify one more time, a square root secant squared theta equals, wait, we can simplify again. A secant theta must be equal to u. Next, we're going to substitute the expression for u into the expression for our missing side. So our missing side was the square root of u squared minus a squared. But we know for this triangle, u squared is a squared secant squared theta minus a squared. Simplify a little bit more. Factor out the a. We have a square root secant squared theta minus 1. And look at that. We're back to a square root tangent squared theta, which gives us a tangent theta. So when we have a triangle, one side equal to u squared minus a squared, that u squared minus a squared is equivalent to a tan theta. Go ahead and complete the same processes for questions A and B. When you think about your domain restrictions, remember we are working with a triangle. So for this problem, we know that our u is greater than 0, our a is greater than 0, and because we have a right triangle, the theta value is going to be trapped between 0 and pi over 2. Let's take a look at our first example. Notice u substitution won't work. Integration by parts won't work. There's no clever algebra that I can do. So what we're going to do is draw a triangle. Let's look at example 1. Notice u substitution won't work. Integration by parts won't work. I'm not sure what will work, but I do see the structures of a square root in my problem. And that is a clue that using a triangle to find my substitutions is going to be very useful. So I draw my right triangle, label theta. Look at the structures of your square root. You have 9 minus x squared. The hypotenuse is always the larger side, so the hypotenuse must be 3. You get to choose whether you want the label for x to be on the opposite side or your adjacent side. I generally choose the opposite side, so I'm going to place x. If all goes well, the missing side should be 9 minus x squared. Fortunately, it is. So, following the process you did in your lesson preview, what do we know? The sine of theta is equal to the opposite over your hypotenuse. So 3 sine theta is equal to your x value. That's going to prove useful because we will have x's that need to be replaced. But we also have a dx. Let's find out what dx is. dx is equal to our 3 cosine theta d theta. So now we're going to be able to replace dx when we're ready. Next, think about the square root of 9 minus x squared. What does that equal? Square root 9 minus x squared is going to be equal to the square root of 9 minus 9 sine squared theta. That can be simplified as 3 square root 1 minus your sine squared theta, which again, we use a trig identity. We'll get the square root cosine squared theta, and we know that then we can replace the square root 9 minus x squared with 3 cosine theta. All right, we're ready for all of these substitutions. Rewriting our integral, we're going to take 9 minus square root x squared, replace it with our 3 cosine theta. X squared is going to be replaced with 3 squared, which is 9, times your sine squared theta. Dx is replaced with 3 cosine theta d theta. Simplify. What do we have now? We have the integral of our cosine squared theta divided by our sine squared theta d theta. Next, rewrite your problem as the cotangent squared theta. So I don't know an antiderivative of the cotangent squared theta. However, I know that the cotangent squared theta can be rewritten as cosecant squared theta minus 1 and d theta. Now the reason that's important is the antiderivative of your cosecant squared is one of your basic antiderivatives that we're all supposed to know. And that will be your negative cotangent theta. Then we're going to integrate 1, so that's negative theta plus c. Okay, feels like we should be done, but notice our answer has thetas in it. We need to have answers with x's. So let's try to get rid of the thetas. Cotangent. So if tangent is opposite over adjacent, looking at my triangle, back to my triangle, the cotangent is going to be the adjacent side of my triangle divided by the opposite side. So I'm going to replace my cotangent minus. Now, where's the theta going to come from? Go back to your sine theta equals x over 3. So if we take the inverse, we know that theta is going to be equal to the arc sine of x over 3. You can write sine inverse, but arc sine actually puts the domain restrictions on the problem that we talked about earlier. So as we completely write our problem, I'd like you to think about how we began. The original problem had a square root involved. And our square root, we could not use u substitution, integration by parts, or any of the other tools that we've worked with before. So that is how. Let's take a look at example 2. Again, I have that square root in the problem. U substitution won't work. Integration by parts doesn't work. You know what? Hey, let's try building a triangle. If we build our triangle for this problem, substitute theta in, notice the structure of the problem is 9x squared plus 4. So that means that the longest side is the hypotenuse will have to be the square root of 9x squared plus 4 because there was the addition. I'm going to label my opposite side 3x and the adjacent side 2. You can follow a different path. That's fine. You get to choose. So for this problem, I'm going to say that the tangent of theta is equal to my 3x over 2. Solving for x, I get x equals 2/3 tangent theta. Now I'm remembering that I need to find dx. dx will be 2/3 secant squared theta d theta. As I look at the problem, I can now replace all of my x's, my dx, but you know what? I'm curious, what do I get if I simplify the square root of 9x squared plus 4? Substitute. Once we substitute, we'll have 9 multiplied by our 4 over 9 tangent squared theta plus 4. Do a little simplifying. We have the square root of 4 times tangent squared theta plus 1. And we know that tangent squared plus 1 is a secant squared, so we get the square root of 4 secant squared theta. And I believe that's 2 secant theta. All right, now we're ready to do our substitution. 1 over your x squared. Your x squared is going to be 4 over 9 tangent squared theta. Then we have our square root. We figured out that the square root is going to be replaced with a, 2 secant theta. And dx, don't forget that dx, that's a very important component, is going to be 2/3 your secant squared theta d theta. Okay, let's clean this thing up. And we will get 3/4 the integral secant theta over our tangent squared theta d theta. So that's not looking familiar just yet, so let's do a little bit of trig substitution and rearrange the problem a bit. So we will have a 1 over cosine for your secant theta. Your tangent is going to be cosine squared over a sine squared, and then we have our d theta. Oh, fun things look like they're going to happen here. If we do a little bit more shuffling around, this comes out to be a cosecant theta times a cotangent theta. And you know that the antiderivative of cosecant cotangent is going to be negative, here's my 3/4, and cosecant theta plus c. Go back to the triangle because I cannot have theta in my problem. Since sine is going to be the opposite over the hypotenuse, the cosecant is going to be equal to our hypotenuse, which is 9x squared plus 4 divided by the opposite, which is my 3x plus c. All right, that wasn't so bad. What an enjoyable problem. We have one more problem that I'd like us to consider. Take a look at it. We have a square root. It's hidden, though, with the rational expression 3/2. Remember, 3/2 is 1/2 plus 1, so that is actually a square root problem. We're going to draw our triangle. For your hypotenuse, let's label it x. We'll also put theta in our problem. And let's see here, we have a 4. So the 4, I can either write a 2 for the adjacent or a 2 for the opposite side. For this problem, I'm going to choose 2 for my adjacent. That leaves me the square root of x squared minus 4 for my opposite side. From here, we can write the expression. Let's see here, we're going to use the opposite over the adjacent. So the tangent of theta is going to be equal, no, I don't want to use the opposite, that's ridiculous. So let's reconsider, because that is ridiculous. I don't want to have the square root in my substitution. All right, so instead, let's have the adjacent over the hypotenuse, which leaves us with the cosine of theta is going to be equal to 2 over x. Solving for x. X equals 2 secant theta. So if x is equal to 2 secant theta, dx is going to be equal to 2. The secant is your secant theta tangent theta, and don't forget good old d theta. Now let's look at our square root. The square root, x squared minus 4. Simplify that. We will have the square root of 4 secant squared theta minus 4. And you've simplified these a few times now. We know this is going to end up with a 2 on the outside. A tangent squared is going to be on the inside. So we'll have tangent squared theta. And we now can replace our square root with the 2 tan theta. Okay, don't worry about those endpoints until the very end. We'll deal with that later. So we'll have the square root of x to the 3rd. Ooh, this is getting rude. So we have 8 secant cubed theta. Your dx is 2 secant theta tangent theta d theta. So now that's all of that is your dx divided by. So in your denominator, remember we have the square roots being replaced with our 2 tangent theta, and all of that is going to be cubed. We have to clean this up just a little bit to give us 16 secant to the 4th power theta. The tangents will, let's see here, we're going to end up with 8 tangent squared in my denominator, and don't leave out your d theta. Now we practice some of the skills from last class. We'll have the integral, pull that 2 out. The secant squared theta looks like a great piece that we could use for u substitution. We're replacing the other secant squared with tangent squared plus 1, and then we will have divided by our tangent squared theta. If we let u equal tangent theta, then your du is going to be equal to your secant squared theta d theta. Rewrite our problem again. We'll have our 2 times the integral. Secant squared d theta is gone. We have u squared plus 1 over u squared du. Clean it up. This is 2 integral. The u value becomes 1 plus u to the negative 2 du, and we're ready to integrate. And we'll get 2 times the quantity u minus 1 over u. All right. Let's go back and resubstitute. So what do we know? This is equal to 2 times your tangent of theta minus your 1 over u, and 1 over u is going to be 1 over your tangent, which is your cotangent theta. And then we will also need to think about our endpoints. Going back to the picture first, replace your tangent with the opposite over the adjacent. So that's going to be x over 2 minus your cotangent, which is your adjacent over the opposite. So that will be 2 over x. And then we'll replace the values we started with. I seem to have lost them along the way. We have 4 and 4 root 3 over 3. Substitute the 4 in, you get 2 times your 2 minus your 1/2 minus 2, substitute in that nasty little critter. We will have 2 root 3 over 3 minus 2, flip it, so there's 3, 4 root 3, and because it's an AP problem, we don't have to do any more. We can stop right there. This problem had a lot going on. That is why it's such a wonderful problem. So review it when you get a chance.